The last question that we want to answer is down here in part E. It says, what month is the estimated temperature 70 degrees Fahrenheit? In what month? So in this case, we're being asked for month, and we're being given temperature. So we want to find X, which represents month, and we're given T, which is temperature. So we're going to go ahead and plug 70 in for our T. So that gives us an equation that looks like 70 is equal to negative 1.36 times x squared plus 17.44 times x plus 23.8. There we go. So here's the equation that we're supposed to solve. Again, we have a quadratic that we're needing to solve. Because of the setup of the quadratic and the fact that the coefficients are decimals, best way to approach this again is going to be the quadratic formula. But in order to be able to use the quadratic formula, our equation must be set equal to 0. So to get that, I'm going to subtract 70 from both sides of the equation. That ends up giving me 0 is equal to negative 1.36 times x squared plus 17.44 times x, and 23.8 minus 70, 60, 50, that's going to be minus 46.2. Minus 46.2. So we have our equation here of 0 equals negative 1.36 x squared plus 17.44 x minus 46.2. Let's identify our A, B, and C. We have here that A is negative 1.36. Our B value, 17.44. Our C value, negative 46.2. So with those identified, we know that they end up getting plugged into the equation. X equals negative B plus and minus the square root of b squared minus 4ac all over 2a. So plugging our values in, we end up with x is equal to negative 17.44 plus and minus the square root of 17.44 squared minus 4 times a, which is negative 1.36, times c, which is negative 46.2. And all of that's divided by 2 times a, which is negative 1.36. So I'm going to start by simplifying everything that's underneath the square root along with the square root. So that gives us second square root. I'm going to go 17.44, square that, minus 4 times negative 1.36 times negative 46.2. Close that off. And you end up with 7.27. 7.27. So x is equal to negative 17.44 plus and minus 7.27. Yep, 7.27, yep. Divided by, if we do 2 times negative 1.36, I believe that ends up giving us negative 2.72. So we now need to find decimal approximations of both answers in here. I'm going to come up here to do that. So we first need to start with negative 17.44. I'm going going to add, for the first time, 7.27, and then divide that by negative 2.72. For that first one, I'm getting 3.74. Okay, so 3.74. And then for the next one, we have to do subtraction. So negative 17.44 minus this time 7.27. Get a solution for that and divide that by negative 2.72. And we get 9.1. Well, because these represent months and months are represented by whole numbers, I'm going to say 4 and 9 are the months. Well, these months for us, 4 would be January, February, March, April. And 9 would be September. So we have that our equation is giving us that the average temperature is 70 degrees in April and September. Can both answers be correct? Yes, because we know that temperature peaks in the summertime. And if we go back up to our data at the very top, we'll notice that in April, 72, in May, 77. So it is going up. We anticipate in June that it'll be higher, in July, and then it'll start coming back down. Now we'll notice, did our estimates perfectly match our data here at the beginning? Well, no, it didn't, because it says that the average temperature in April is actually 72, not 70. But again, our model is not perfect. It doesn't model the data exactly. Furthermore, we'll probably end up with model breakdown, because we know that a quadratic looks something of this nature. And we know that once the year comes to an end in December and you get back to January, that the temperatures will actually start going back up. In a quadratic model, you're going down forever. You never come back up. So in this case, a quadratic model may only be good for modeling over a short period of time. In fact, it is only good over a short period of time. If you want to model continuously over the years, I'm probably going to need a different model. So we will easily experience model breakdown in this example, but it does do a good job modeling our confined data set.